All right, good morning, everyone. Hope you're all feeling good. So Friday today, so homework due tonight. And then next week we will do lab number 3. So there is a pre-lab number 3, so please complete that pre-lab before you go to your lab. And then finally, if you're going to participate in the hands-on bonus project for up to 3 bonus marks, then you have to email me your project idea by Monday at midnight. And so if you don't remember what the hands-on kind of bonus project is all about, just go to the course syllabus. There's like a whole page that describes it. So you can read about all those details in the course syllabus. All right, so what we were working on last time, last time we had a bit of a diversion. We did conductors and electric fields. In Monday's class, we were talking about moving a charge through an electric field and calculating the work done as we move that charge. And so the example we thought about was we place a charge, capital Q, in some position, and it establishes an electric field in that region of space. Then we take a second point charge, little q, and we start it at position 1, and we move it to position 2. And we are going to calculate how much work was done. And we did that calculation for 2 different paths. And what we discovered was that the work done did not depend on how you go between points 1 and 2, only on the initial and final position. So the work done by green path 1 and purple path 2 were identical. And you could make any path between points 1 and 2, and you would calculate the work, and you'd always get the same result. So work, roughly speaking, is force times displacement. If your force is not constant and there's some kind of angle between your force and your displacement, then we had a more kind of rigorous way of doing that calculation. It was this integral of F dot ds. And the work kinetic energy theorem says that that work that you calculate is equal to the change in kinetic energy. For our example of a point charge moving in the electric field established by a second point charge, we calculated the work, and this was the result that we got in the red box. So it's Coulomb's constant times Q times the product of the charges, and then it was multiplied by 1 over R2 minus 1 over R1, and there was an overall negative sign. One thing we said right at the end of Monday's class was that when the work done by a force is independent of path, we give that a special name. It's called a conservative force. And the reason it's called a conservative force is because we can then define a potential energy associated with that force such that the sum of the potential and kinetic energy would always be constant. Or another way of saying that is if you took the sum of the change in kinetic energy and the change in potential energy as you move a particle from one position to another, those changes would add up to 0. So the idea is I can take kinetic energy and I can transfer it to potential energy, or I can take potential energy and transfer it to kinetic energy, but the sum of those two would always be the same. Okay, and so that's what we're going to try to do. We're going to say, all right, so we know that the change in potential plus the change in kinetic energy is going to be equal to 0. But the change in kinetic energy is equal to the work. The change in kinetic energy is just equal to the work. And so for the work, we can substitute it in here for the change in kinetic energy. And so we'll do that. So it's plus minus KEQQ 1 over R2 minus 1 over R1. And I guess I'll put this all in square brackets there. So we have plus some negative quantity. And of course, all we need to do in order to find this change in potential energy is move everything that's not delta U over to the right-hand side. And so therefore, we can say the change in potential energy is, let's see, delta U, which is the potential energy at the final position 2 minus the potential energy at the initial position 1 would have to be equal to, well, we just take everything and move it to the right-hand side. KEQQ 1 over R2 minus 1 over R1. Okay, and so what we can see is that there's two terms on the left side and on the right side. On the left, our two terms are the potential energy at the final position minus the potential energy at the initial position. And on the right, we have a term that involves R2, the coordinate at the final position, and then the other term involves R1, the coordinate at the initial position. And so what we're going to do is we're going to associate the final potential energy with the coordinate at the final position and the initial potential energy with the coordinate at the initial potential energy. And then what we end up with is this expression for the potential energy between our pair of point charges. Our system was just a pair of point charges, and so we can say for our system of 2 point charges, let's say separated by distance r, we have that U is KEQQ divided by R. And so if we're at position 1, we would have U1 is equal to some constants divided by R1. If we're at position 2, we would have U2. The potential energy at position 2 is some constants times 1 over R2. Okay, so this is the potential energy of a pair of point charges, Q, little q, and capital Q. Okay, so one thing I just want to point out, we won't write it down, but this potential energy is just only associated with the position of our charges. So if I have fixed charges, little q and capital Q, and then I just move them around, the only thing that the potential energy depends on is the distance between those 2 point charges. That's just like the gravitational potential energy. If I take my pen, it has gravitational potential energy mgh, the distance above the ground, and if I move it around, the only thing the potential energy change depends on is how high am I above that ground. So the potential energy depends on the positions of our charges. Kinetic energy, as you know, is 1/2 mv squared. It depends on how fast our objects are moving. Okay, good. So what I want to do is I want to think back to when we defined electric fields. Remember, we started our discussion of charges and the interaction between charges by writing down Coulomb's law, the force between 2 point charges. And then we said, well, another way to look at that is to say, let's imagine we take one charge, we put it in some position, and then it establishes an electric field in that region of space. And then we introduce a second charge. One way to think about this is that the force on the second charge is due to the electric field that was established by the first. Yeah. Oh, sorry. Here, let me change this while I still talk. What we're going to try to do is we're going to try to do something similar for the potential energy. We're going to say, I'm going to take one charge, I'll place it at some position, And then it's going to establish what we're going to call an electric potential in our region of space. And when I place a second charge nearby, it interacts with that potential due to the first charge. And we can use that to then calculate the potential energy. So let's see if we can figure out how all that works. Okay, I think we're back in business with the mic. Okay, so I'm going to make a little table here. And so on one side of our table, we're going to have the potential energy of a pair of point charges. We just worked that out. And what it was U was KE Q times Q divided by R. On the other side of my table, I'm going to put the force between a pair of point charges. Okay, so it was F was Coulomb's law, it was Q divided by R squared. Force is a vector, so it has a direction, and so we'll specify the direction with that unit vector R hat. Okay. So what we did for force is we said, let's imagine that Q establishes an electric field that then exerts a force on little q. All right, so we did that, and we defined the electric field to be Ke big Q over R squared R hat. Another way to think of it is if we just take the Coulomb's law force and divide by little q, that gives the electric field. Or we could then say the force on little q is Q times the electric field due to the large charge. Of course, we can do it the other way. We can say little q makes its own electric field, and then it exerts a force on big Q. That's exactly the same thing. So we're going to try to do something analogous for this potential energy. So we're going to imagine that big Q establishes an electric potential. This electric potential, we're going to give a symbol to V. Another word for this electric potential is voltage. So when we eventually start talking about circuits, we'll talk about the voltage provided by a battery. That's the same thing as an electric potential. Okay, so established is an electric potential that interacts with other nearby charges. Okay, so V, this electric potential or voltage, we're going to get it just by taking this potential energy and dividing by little q. And so it's just going to be Ke big Q divided by R. And so this is the electric potential due to big Q. And so then the potential energy between the pair of point charges is just going to be little q times V. So this is going to be the potential energy of little q in the potential of big Q. Okay, and then of course we could do the opposite. We could say, let's place the small little q charge. It makes an electric potential that then interacts with the large charge, capital Q. Okay. So all of this stuff that we put in the table is relevant for the interaction between point charges. But we've seen that we could have some more complicated scenarios, right? We could have a charged rod. So how do we write down the potential due to a charged rod? Or we could have a charged sheet. How do we write down the potential due to like that charged sheet? So let's see if we can be a little more general about this. So what we're going to try to figure out is calculating changes in potential. So this will be changes in potential will be delta V from electric fields. Okay, and this is going to be actually fairly straightforward because we've done a lot of the hard work already. So we're going to start with the work kinetic energy theorem. Okay, so the change in kinetic energy is equal to the work, and the work is F dot ds. Okay, but we know that the change in kinetic energy is also equal to minus the change in potential energy, just because delta U plus delta K has to be 0. So they have to be opposite of each other. Okay, so we can rearrange this and let's write delta U is equal to minus this F dot ds integral. Okay, and so this is completely general. This could be like, I don't know, a gravitational potential energy or electrostatic potential energy or anything else that is a potential energy, like a spring potential energy or something like that. So now what we want to do is we want to be specific to charges in electric fields. So for a charge in an electric field, well, we know that the force is going to be Q times E, right? I place a charge in an electric field, the force it experiences is just that electric field times Q. And we've just worked out now in our little table that we could express potential energy in terms of Q times an electric potential. And so what I'm going to do is we're going to make these substitutions into this expression that we got from the work kinetic energy theorem. So let's see. Delta U, we'll write Q delta V is equal to minus this integral. For the force, we'll write that as Q times E, like so. And so now you can see that what we've got is a Q factor on both sides. And so we could cancel. And then delta V is equal to minus the integral of E dot ds. So this is how we could calculate a change in electric potential from an electric field. Okay, so there's a few different possibilities. Let's work out one of the easiest cases. How can I make this integral as easy as possible to solve? What would I want for my electric field? Yeah. Make it constant. Okay, let's do that. So we can make a constant electric field. So let's do an example. By taking, say, a positive plate, and maybe what I'll do is I'll put a negative plate over here. Whoops, sorry. And something that we saw maybe last week or 2 weeks ago or something like that was that the electric field between two charged plates is constant, and over here, E is equal to 0. So E is equal to 0 outside the plates, and here E is equal to a constant. And so what we could imagine then is taking a charge, we'll start at one position, and then we'll move it to some final position. So let's call this position 1, this is position 2, and let's say we move this a distance d. Okay, so we're going to go from 1 to 2. We're going to move a distance d. And the other thing we're going to do to make this calculation simple is I'm going to make my displacement ds in the same direction as the electric field. Here, I forgot my vector sign over my displacement. Okay, so our ds in this case is in the direction of the electric field. So for E parallel to ds, E dot ds is just equal to E ds. It's E ds times the cosine of the angle between the two, but the angle is 0 and cosine of 0 is 1. Okay, so that means delta V is equal to minus the integral of E dot ds is just E ds. The electric field is constant, so we take it outside. So since E is constant, we can factor out of the integral. Okay, so then what's the integral of ds? It's just adding up all the little displacements to go from 1 to 2. What would that give? In our little figure there, d, that's right. So we just add up all the small displacements to go from 1 to 2, and that would just be equal to d. And so for a constant electric field, we have that delta V is equal to minus E times D. Okay, we can think about this just for a second. When we went from position 1 to position 2, our potential decreased. So that must mean that we started at a region of high potential and then went to a region of low potential. So then the change of potential is final, which is low, minus initial, which is high. And so we get a negative change in potential. So notice that when we move in the direction of the electric field, the change in potential, delta V, is less than 0. It's negative. So that must mean that electric fields point from high to low potential. All right, so let's draw this picture again. Here's plus, 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 charge positive plate. Here's our charge negative plate. Here's our electric field. And so what we've just deduced is that over here by the positive charge, we have a high potential. And then over here, close to the negative plate, we have a low potential. All right, we could think a little bit more about this even. So if we had a charge Q in here, and we move it from position 1 to position 2. Well, let's see, the change in potential energy. Let's calculate the change in potential energy. Delta V is equal to, sorry, what I want to do, I want the change in potential energy. Delta U is Q delta V. So if I take my charge and I let it move from 1 to 2, let's say little q is positive. Do I expect the charge to gain or lose kinetic energy when it moves from 1 to 2? Yeah, go ahead. Gain, right? We can think of it in a couple ways. It should be repelled from the positive plate and attracted to the negative plate. And so there's going to be a force that's moving it from 1 to 2. It's going to accelerate, it'll gain speed, and therefore kinetic energy. Another way to think of it is there's an electric field. It exerts a force that moves it to the right, and so it should gain kinetic energy as it moves to the right. So we expect Q to gain kinetic energy as it moves from 1 to 2. If it's gaining kinetic energy, it must be losing potential energy because energy is conserved. So therefore, it must lose potential energy. And so delta U is Q times delta V. We calculated delta V, it's minus E times D. Minus E times D. And so this is minus QE times D, which is less than 0. And so that works. Okay, we could have said, well, what if our charge was negative? Well, then it would be attracted to the positive plate, repelled by the negative one. And so if it had some initial velocity towards the negative plate for some reason, we gave it a kick, it would slow down as it approached that negative plate, and it would lose kinetic energy, and it would gain potential energy. And this same expression, minus QE times D, still is valid. It's just that the charge we put in there would be a negative charge, so that overall, this change in potential energy would be positive. Okay, so the other thing I want to do today is I want to think about how we can calculate an electric field if we know something about how potential is changing in space. So we've talked now about how to calculate changes in potential from electric fields. Can we go the other way? So calculating electric fields from potentials. Okay. So what we're going to do is we're going to consider a point charge in an electric field. Okay, so let's see. Let's suppose our point charge is following some path, okay? And then we end up with our charge at some position over here. And let's suppose that it's moving with some displacement ds in this direction. And at this particular point in space, there's some electric field. We'll draw it in some arbitrary direction. So let's say our electric field is something like this. And so here is theta. Okay. What I'm going to do first is I'm going to break this electric field up into components. I'm going to pick one component that is along the direction of the displacement, and I'm going to pick a component that is perpendicular to that direction. So let's see, I'm going to drop this down so that we get a perpendicular. Okay, so here is going to be ES. E sub S corresponds to the component of the electric field in the direction of the displacement. So component of E in the direction of ds. Okay, and then there's another component that is something like this, and I'll just call this one E perpendicular. Turns out we're not going to be interested in E perpendicular. For the argument that we're about to make, it's going to be this ES component that we want to focus on. Okay, so from the work kinetic energy theorem, the work kinetic energy theorem, it just keeps giving, right? We just keep starting at the same place and we just derive different things from it. So let's see. I want to imagine that we take a very small step, delta S. We'll make our step so small that even though our path is not straight, even though the electric field may not be constant, if we make our step small enough, we can approximate our step as being in a straight line and the electric field being uniform over that small distance. And so even if the electric field is changing very rapidly, we just make our step smaller and smaller and smaller until this approximation works. So if we do that, the change in kinetic energy is F dot delta S. And so this is going to be a small step. Okay, so this is a little charge Q. So the force is just going to be Q times E. And then we have to do our dot delta S. Okay. And what about the left-hand side? The change in kinetic energy, we could write as minus the change in potential energy. All right. So what's next? The change in potential energy is Q times the change in electric potential. Okay. And then so over here, we're going to have Q. And then we have a dot product. So we could write that dot product as E delta S times cosine of theta. Okay, so fair enough. We could cancel the Q's. That's really the advantage of defining this electric potential and the electric field as being independent of this little Q, because now we get these cancellations. All right, so then we have delta V is equal to, I'll put the minus sign over here, and then I'm going to write this as E cos theta, and then we'll have our delta S. Okay, well, let's go back to our picture here for a second. What is E times the cosine of theta? It's the component of the electric field that is adjacent to the angle theta. And so that's just ES. This is ES, the component of the electric field that is parallel to our displacements. So therefore, let's see, what we have is delta V is equal to minus ES delta S. So the last thing I want to do is I want to solve for ES. I guess I moved over the negative sign when I didn't have to, because I'm about to move it back. So let's solve for ES, and it is minus the change in potential divided by the change in position. We said that our change in position was going to be a really small change in position. So what is this ratio in the limit that the delta S goes to 0? It's just the derivative, right? So in the limit that, delta S goes to 0, we would have ES is equal to minus dV ds. So this is the component of the electric field in the direction of S. So if I wanted the electric field in the X direction, I would evaluate dV by dx. And then you'd have to put a minus sign. Then if I wanted the Y component, I would do minus dV dy. And if I wanted the net electric field, I would just take those two components, square them, add them up, and get the square root, Pythagorean kind of theorem. So what we've done now is we've shown that there's this relationship between electric potentials and electric fields. The change in potential is given by an integral of the electric field. The electric field is given by a derivative of the potential. In lab number 3, which you'll do next week, this is exactly the kind of thing that you're going to do. I won't write it down, but I'll describe it to you. So you're going to use a little multimeter to measure voltages. Those voltages are exactly this electric potential V that we've been talking about. So you're going to have a carbon paper. So it's paper that has like carbon stuck to it. Carbon is conducting, so it'll allow charge to flow around. Then you're going to take a power supply. It's going to provide some output voltage. It's exactly the same thing as a battery. And on this carbon paper, there's going to be little conducting electrodes. It's silver paint, so they paint different patterns on the carbon paper that make these electrodes. And then you apply a voltage to them. Maybe I'll draw one. So lab number 3. So you have your carbon paper. So carbon paper. And then there's going to be some electrodes drawing on them. I'll draw a simple one. So these are going to be electrodes drawn using silver paint. Okay. Then you're going to take a power supply and you're going to take, I'll draw it as a battery. So this is a battery or a power supply. It's a source of potential difference. You'll take one of your terminals from your battery or your power supply, and you'll attach it to one of the electrodes on the carbon paper. And then you'll take the other one and you'll attach it to the other electrode. So I'm using a red wire for the positive terminal of the battery and a black wire for the negative terminal. That's sort of convention. Okay, and so what this essentially does is it stores a bunch of positive charge on the left electrode and negative charge on the right electrode. And then you're going to take a multimeter, you're going to set it to measure voltage, and you're just going to measure voltage at a bunch of different points on this paper. And you're going to map out how the voltage is changing as a function of position. Okay, and so it's going to be a lot of measurements, but it's very simple. You just take a little probe, press it on the carbon paper, read the voltage. Okay, so we will map out the potential or voltage on the carbon paper. Okay, that'll be the first step. And then you'll kind of play with different ways of actually visualizing what that looks like. We're going to use like these color plots to visualize what the map of potential looks like. Then what you'll do is you'll say, okay, for every point that we've measured the potential at, I could calculate the components of the electric field. I could calculate the X component of the electric field by taking the ratio of how the voltage changes in the X direction divided by the size of the step that I make in the X direction. And then you'll calculate how the voltage changes when I step in the Y direction, and those ratios will tell me the Y component of the electric field. And then finally, you could say the net electric field will be EX in the I hat direction plus EY in the J hat direction. And so now you know the electric field at that point, and you're going to do that calculation. Well, there'll be some, they'll be given some assistance through some function that will do that calculation for you at all points on this paper, and you'll be able to map out both the electric potential and the electric field. In this case, what you would find is that the electric field would be approximately uniform between these two electrodes, which act a bit like these conducting sheets or these charged sheets that we've been talking about. Okay, so that's the goal for lab number 3. So let's talk about one more thing. We have about 10 minutes left. So we've talked in general about the relationship between potential and electric field. Let's see if we can kind of think about point charges. So let's return to a point charge, capital Q. Okay, we know that the electric field due to this point charge is KEQ over R squared, and the electric field points in the radial direction. And now we've worked out that the electric potential is KEQ over R. Okay, so what I want to do is I'm first just going to draw the electric field, and we all know what that's going to look like. So let's take a positive point charge, capital Q, and we'll draw the electric field. Whoops. We'll draw the electric field like this. So it's just a radial electric field. Nothing unexpected or new here. All right, what I'm going to try to do now is I'm going to try to draw lines of constant potential. So to this plot of the electric field, we're going to add lines of constant potential V. These are usually called equipotential lines. Oh, I didn't spell that right. Equipotential lines. I've called them lines, but I call them lines because I'm going to draw a line. But really, this electric field is 3-dimensional, and the constant lines that we're going to draw on our 2D screen really represent spherical surfaces. So it's really, it's a surface of constant potential. So If V is equal to KEQ over R, what should my equipotential lines look like? The only thing that the potential depends on is the distance from the charge. So if I want to have a constant potential, what should I do to that distance? How could I maintain a constant distance? If I wanted to walk a path around this charge and keep a constant distance from it, what kind of path should I follow? A circular one. And so I should put the charge at the center of my circle. And so here is a circular path around that charge. And so this would be, let's make a little legend here. These are equipotential lines. And this is the electric field. Okay, so that's one equipotential line. I could draw more. So this one would be like this. So it's just another concentric circle. This would be a potential V1. This would be potential V2. Now I'm going to draw a third one. But what I want to do is I want the change in potential between neighboring lines to always be the same. So, for example, between the two that I've drawn, I would have a change of potential of V2 minus V1, whatever that is. So, should my third, if I want to have V3 minus V2 be equal to V2 minus V1, should my third line be equally spaced? Should it move further away or should it be closer to V2? What do you think? Closer? Okay, let's think about this for a second. Delta V is equal to minus E dot ds. So if the electric field is very large, right? If E is big, then delta V is also big. If E gets small, then the change in potential gets small. So out here, when I'm far away from my charge Q, the electric field is getting weaker and weaker and weaker. And so if I want to have the same change in potential, I have to take bigger and bigger and bigger steps. Okay, and so my V3 would be out here, and I would be a little bit further from V2 than V2 is from V1. Okay, so this expression suggests that for the same ds, delta V gets smaller as E decreases. So to maintain a constant delta V, we need to take larger steps as E gets weaker. Okay, and so what I've tried to draw here is that delta V equals V3 minus V2, and delta V is equal to V2 minus V1 are the same. And in order for us to do that, the spacing between equipotential lines has to get bigger and bigger and bigger as the electric field gets weaker and weaker. There's 1 minute left. Let's draw one more example. Let's draw the example that we talked about. these parallel sheets of charge. We already know that the electric field is pointing from positive to negative, and that the electric field is constant. If the electric field is constant, if its size is not changing, what should the spacing between the equipotential lines look like? They should be, yeah, constant spacing, right? We said that to maintain a constant delta V, we need to make the spacing between our lines bigger as the electric field gets smaller. But if the electric field is the same everywhere, then my spacing should be equal. So these are equally spaced equipotentials. Since E is constant between our charge sheets. Okay, so you'll do these kinds of things in lab 3 next week. It's a pretty fun lab, I think. So I hope you like it. Have a good weekend.